Okay, welcome to my presentation about constraint-based uncertainty bounds for transient groundwater flow under equifinality. This is research done with my colleague Xenia Bestutseva from the Zuse Institute in Berlin, who advised me on the mathematical programming aspects of this research. To begin, let us motivate this presentation. So the subsurface plays a very important role in many societal topics. This reaches from water supply to infrastructure through deep construction sites, for instance, and the energy transition through topics such as geothermal engineering, shown here on the right. The challenge with these is that if you want to implement any of these operations safely and efficiently, it's very important that we understand the system in which we operate. And this is not an easy task, because the subsurface is an extremely complex and heterogeneous environment shaped over millennia of geological processes. At the same time, insights into the subsurface are quite scarce. So often we only have a few geological cores and maybe some observation wells, but usually this information will not suffice to derive unique characterizations of a subsurface, which basically means that while something like this could fit the observations we have made, so could many other possible characterizations, including some that may have implications negative for our operations that we might not have anticipated. So it's very important that we quantify the uncertainties in the system rigorously. A little bit more formally, the issue that we're encountering is known as non-identifiability. You can see here on the left side a very simple numerical model, steady state, two-dimensional top-down view. We have a recharge boundary in the north and a fixed head boundary in the south, as well as two hydraulic head observations that we want to fit. Now, if we were to naively try to solve inverse problems in order to figure out which hydraulic connectivity field could have generated these hydraulic head observations, we will quickly realize that there's a lot of different solutions we could find. This could reproduce the observations, and so could something like this, or something like this, or something like this, or something like this, or even something like this, which are the lottery numbers of Eurocheckpoint 2 weeks ago. So the message I want to convey with this slide is that basically in an underdetermined system, you can fit whatever the hell you want. And this, of course, has severe implications for uncertainty quantification. Because we have limited numerical resources, we cannot find all of these infinitely many possibilities. And since most of the uncertainty quantification we do relies on random sampling in one way or another, the consequence of this under-exploration of possibilities is often an underestimation of uncertainty. This, in turn, can lead to overconfidence in the decision support we supply, because there might just be some risks we will never find. And this is obviously something very negative for what we're trying to do. So in this study, we want to take a look into if there are methods that maybe can represent and quantify uncertainties without the need to resort to random sampling. Before we go into how we want to achieve that, let's first take a look at the problem in a little bit more detail. I mentioned before that a lot of the uncertainty in groundwater models comes from non-identifiability. The simplest way to see that is perhaps in a system such as this one, where we would have a confluence of two rivers, QA and QB, that form a third river, QC. We might know how much flow the combined outflow carries, but if you want to infer how much water flows in each of its tributaries, QA and QB, then there will be no unique solution, no unique answer to this question. For instance, if we know that the combined outflow carries 5 cubic meters per second, then a valid solution would be that one river carries nothing and the other river carries everything. But likewise, a combination of 1 and 4 cubic meters per second, or 2 and 3, or 3 and 2, or 4 and 1, or 5 and 0, would all be equally valid solutions to fit the data we have. Now you might notice that all of these solutions here lie along a straight and diagonal line in this variable space. And as it turns out, this line of equivalent solutions is aligned with the so-called null space. This is something that emerges in linear systems, and is also something that has been exploited for uncertainty quantification in the past, chiefly by the work of John Doherty and his colleagues, where they use this kind of methods for more efficient sampling in uncertainty quantification and parameter estimation. So this line is obviously very interesting for us in uncertainty quantification, because it basically tells us which solutions we cannot distinguish based on the data we have. Now there's another perspective we could take on this problem, and this one comes from mathematical programming. in mathematical programming, which would basically reformulate the system as a system of constraints, which essentially enclose a feasible region shown here in orange. And if you do so, then you might see that we get basically the same answer we had before. We again have this orange line that encloses all solutions that fit our assumptions. Now, this mathematical programming has a really nice advantage in that it's a little bit more flexible than the null space perspective. For instance, the outflow doesn't necessarily have to be a fixed number. It could also be an interval, just like QA and QB. And if we do so, the two inequalities that currently form the diagonal line relax a little bit and form this kind of trapezoidal feasible region. And again, this feasible region is very useful for uncertainty quantification because it contains all the solutions that fit our initial assumptions, our physics, and, as you shall see later, our data. If we were to try to do sampling, for instance, all the samples would lie in this feasible region, right? If we had a solution where QB carries more flow than QA, it would lie somewhere in the top left. If both rivers carry equally much flow, it would lie somewhere in the middle. And if QA carries more flow, it would be somewhere here in the bottom right. Now, in normal ensemble-based uncertainty estimation, we would basically try to find as many of these different possibilities as we could and hope that they explore the extent of that feasible region sufficiently. But that's a very tenuous proposition, especially in high-dimensional settings where the feasible region can be an extremely high-dimensional shape. And at the same time, of course, the representativeness of every single realization reduces. So we would basically never be able to explore the entire region exhaustively, randomly, as long as we have finite computational resources. Now, what you could do instead is that we could try to study the geometry of that feasible region. And if we, for example, learn how far it extends along each of the dimensions of our variable space, then it could give us an indication which ranges of variables can be supported with our assumptions. To this end, fortunately, there are a number of really interesting properties we can explore. One of them is that if our system of constraints is linear, then the resulting feasible region will be a convex polytope. This is very attractive for optimization because if we solve a linear optimization problem over a convex polytope, then the optimum will always lie on the hull of a feasible region. In fact, most of the time, it will lie on one of its vertices, which is something you're seeing here on the right side. There's a branch of mathematics that exploits these properties for really efficient optimization, known as linear programming, which will form the backbone of the research we're presenting in this, this talk. Because if we can solve optimization problems efficiently, one of the things we could do is that we could simply try to minimize and maximize every single uncertain variable. And as we do so, we are basically tracing the extent of a feasible region. And this knowledge then allows us to go back to our initial bounds and, if possible, tighten them. In doing so, we're learning something about variable ranges that are impossible. And this is conceptually also somewhat similar to what we're doing in statistical inference, where we are simulating data to reduce uncertainty. Something very similar happens here as well. This approach of using minimization and maximization operations to tighten bounds is known as optimization-based bound tightening. And this also isn't exactly new, but is so far, to my knowledge, mostly been used for optimization problems. And we in this study want to propose its use for uncertainty quantification. Now, this has all been relatively theoretical, but how can we actually use that for hydrogeology? Well, in groundwater models, we have a lot of equality constraints that we must maintain. For instance, if we define a numerical grid over our area of interest, we know that in every grid cell, the mass balance must be maintained. Water flowing out of a cell must equal water coming in a steady state system. In a transient system, we would also have storage terms that would add to this mass balance. But the bottom line is that this would always be a linear constraint, so it fits very nicely in this framework. The second equality constraint we usually have is Darcy's law, which relates the volumetric flow to the hydraulic heads through a product between the flow active width, which is a constant depending on grid geometry, as well as the hydraulic head gradient and the transmissivities. Now, Darcy's law, while an equality constraint, is unfortunately no longer linear, because on the right-hand side here we have a product between two unknowns, the transmissivity and the head gradient, which makes this constraint bilinear and hence nonlinear. Now, unfortunately, non-linear equality constraints make the feasible region non-convex, and with it, we lose a lot of the numerical efficiency that makes linear programming so elegant. And for uncertainty quantification, we really want to maintain this efficiency. Fortunately, there is a workaround known as a so-called McCormick relaxation, which replaces this product with 4 linear inequalities where in each of these inequalities, one of the terms in the product is replaced with the current lower or upper bound of that variable, which basically turns them linear again. Now, this doesn't come for free. It makes the feasible region convex, but it's sort of makes the physics a little bit more fuzzy, a little bit weaker. And that has negative consequences, especially when we go to 2-dimensional and transient settings. Unfortunately, this detail doesn't fit into this presentation for time reasons, but if you want to read more about it, the preprint we will share at the end of this presentation investigates this issue in a lot more detail. Now, to finally, in the time that remains, let us demonstrate the performance of this optimization-based bound tightening in a simple 1-dimensional groundwater model. This model is steady state. It is 10 cells where we have water flowing in on the left side and water coming out on the right side. There's no water added or removed in between. We also assume that we have 2 hydraulic head observations, and the way that we integrate these in optimization-based bound tightening is that we are basically taking the hydraulic head intervals and collapsing them onto the observed values in this framework. We assume that we don't know the exact hydraulic heads, we don't know exact transmissivities, we don't know the recharge values, and we don't know the volumetric flow. We basically let optimization-based bound tightening infer those from the physical equations and the initial bounds we are prescribing. If we do so, we can see that the initial bounds, shown here in gray, quickly tighten to yield the tight blue intervals that we see here at the end of the animation. Because that may be a little bit confusing, let's take a closer look at these frames. The first thing we see is that optimization-based bound tightening identifies physically meaningful information. For instance, it learns that the flow has to go from left to right, from the source to the sink. We see that the flow has to be uniform because no water is added or removed in the middle of it, and it has to be positive, accounting for the left to right flow direction. We also see that it figures out that the hydraulic head levels have to drop from left to right accordingly. And specifically, we notice that it realizes that you have to thread your hydraulic heads through the observations. So it notices to the left of the first observations, hydraulic heads can't be lower. And to the right of the second observation, they can't be higher, as that would conflict with Darcy flow. The second thing it learns is that the mass balance in the entire system must be maintained. We gave it deliberately mismatched recharge bounds, and it learned that you cannot take out more water than you put in a steady-state system, and it adjusts the recharge bounds accordingly. Finally, it learns that the transmissivities have to be tightened, especially the lower bounds have to be raised. This should also make sense because since we are putting in a certain amount of flow, if the transmissivities are too low, then the flow could only be supported through hydraulic head gradients that might be larger than what the observations and the initial bounds support. And to avoid these unphysical results, the transmissivity bounds have to be raised, the lower ones, to prevent this from happening. Now, of course, these bounds may be a little bit difficult to believe without verification. And so one of the advantages of the simple 1D steady state setting is that we actually can sample the feasible region randomly and directly. If we do so 1,000 times and we plot the samples over intervals, we see that the random samples, the exact samples, never lie outside of the bounds that optimization-based bound tightening gives us, which basically confirms that OBBT provides us with safe outer bounds on the feasible region for all the unknown variables we have, which I think is quite exciting. With this, we're at the end of the presentation. If you want to take some things away from this talk, I hope it will be the following. The first one is that optimization-based bound tightening provides safe outer bounds on the feasible region, which basically gives us safe, conservative estimates of uncertainty arising from non-identifiability, which I believe is one of the greatest sources of uncertainty in groundwater models. And this fact that the outer bounds are safe makes optimization-based bound tightening also a very powerful tool for certification. For instance, for proving negatives, such as proving in a court case that a pumping rate that you plan to implement at a certain site will not lower the water table in some other nearby environmental protection zone, for instance. So I think this might be a very useful tool for court cases, or as a complement for ensemble-based uncertainty quantification, where you could basically use it to verify that your ensemble has explored the feasible region sufficiently. Of course, there are some challenges and limitations. So one thing I hinted at before is that the McCormick relaxation causes issues when we move to 2D or to transient settings, specifically because it breaks the irrotationality of groundwater flow. There are ways to restore that with some trickery, but these are details that I will defer to the manuscript that we will show on the right side in a little bit. A second challenge is that computational demand of a method is relatively high. For the 1D model I've showed here earlier, the bound tightening takes about 15 seconds, but if the grids become significantly higher dimensional, this computational demand grows quickly. And for a system with 10,000 variables, for example, you probably would have to go to a supercomputer. Now, at this day, research is still at like a proof of concept stage, so I'm very confident that there's many options for improvements that yet to remain that we haven't yet explored. So this will hopefully improve in the future. If you want to learn more about this research, I would like to defer you to our preprint available on the archive under this QR code or under this link. And with this, I want to thank you for your attention. And if you have any questions, feel free to send me an email or talk to me at the conference. Thank you.